Right, folks, are you able to hear me? So one thing, guys, as I'm recovering this website, I do apologize that my video recordings and many things are not properly organized on the course portal. And I am putting in, we are trying to put it all updated in an organized way. All I can say is the content has come back. It's rather disorganized. Things are here somewhere, and sometimes they're not even here. So I will be spending maybe the lunch break, and I'll try as much as I can to make sure that everything is back in its place. Like, for example, many of you pointed out that in the course, where are the videos, right? So these videos have taken a hike, it seems. I don't see the videos myself for all of these sessions. So I'm going to add those back. In fact, you see empty boxes instead for those videos. I'm going to bring all of those back, guys. You will see those videos back again. Give me some time. So today's topic is actually, now we change from prompting and from RAD to a new topic, which is fine-tuning. We are now entering the very important topic of fine-tuning models. So before I go into fine-tuning, I'll ask this question. What does it mean to fine-tune a model? Anybody? Arun.
Reinforce some of the weights that you are interested in, so we can get a more focused training of the model.
Yeah. Is it unique to neural networks, or can we fine-tune anything? Yeah. Fine-tuning just means that if you have a model that has gone through partial training, you can continue the training of the model. So I will now just do some writing now to explain this concept or the broader concept of transfer learning, fine-tuning. Let me explain it with a bit of writing. Now, I do know that most of you are aware of, one second. Most of you are aware of this, excuse me, about, I have to get this thing back. Are aware of these concepts, so forgive me if it looks like a elementary repetition for those of you who know this, and it's for the benefit of those who are new to this topic. So, any questions before I start?
So fine-tuning is not just adding knowledge, right, Asif?
No, fine-tuning is more than that. So that's exactly the topic I'll cover, Jay, now.
Okay.
See, guys, just let's go back to 101 basics. When the traditional machine learning cycle is, you start with a hypothesis. This is something very basic. You want, let's say that you have data like this. Suppose I were to take data like this, and I were to try and fit a model to it. Right? You could fit a model. Your model could be like this, right? Something like this. And then you may say that, let's make this model better. And then you may start saying, let's say this. This is the basic intuition people have of fine-tuning. That let's say that your model is mostly right. The word fine-tuning means you sort of turn the knobs a little bit in the weights and if you think of the weights and biases as little knobs on your machine, you're just tuning it. And the word, I suppose, comes from, like, if you're a car enthusiast, right? That's what you do, isn't it? The manufacturer gives you a car. Let's say that you own one of these sports cars, right? You're never happy with the way the car comes from the manufacturer, right? what is the first thing you do the moment you get the car? You immediately open the hood, isn't it? And then you go at it, right? You start, you say, well, this governor is speed limiting me. Let's get rid of the governor. Let's do this. Let's do that. Isn't it? You even change the basic oil. You put a low viscosity oil for better acceleration and all of that. We all do that. That is fine tuning. Quite literally, that's fine tuning. Right? Now, in the way we would think about it in machine learning is, suppose you have data and you start with in the beginning, you have data. Let's say that this is your data. This is the set of data. It contains your labels xi and yi, xi being a vector and yi, the target space. Right? The target space could be a categorical for classification, or it could be regression, a number. Right? And I'll take, just for fun, I'll take supervised learning as an example. And then you start fitting a model. Suppose you were to fit, let's say I take this example, and you try to fit a third degree polynomial, a very simple third degree polynomial. You know that if you start with a random set of values, let's say that you, and again, I'll just take this. Suppose you take, in terms of weights and biases, you take a weight 0, or let me just call it a bias term, b plus w1 x plus w2 x squared plus w3 x cubed to this data. You randomize the weights. What will your curve look like? Your curve may look like something like this, the blue curve, isn't it? Are we together? That is your untrained model. Untrained model. Now, every time you take a mini batch, and we talked about mini batches of data and so forth, you take a mini batch of data and you go through one epoch. What is the journey that you do? You take a mini batch, and with the mini batch, you feed it through the model. It goes through the model, the little batch. It goes to the model. It produces the y hat for the batch, right? You get the you get this collection of y hats. You compare the y hat to the actual y's, the actual labels, ground truth, and from that you realize that oops, and we don't usually call it oops mathematically. What do we call it? We call it loss. The loss function. Loss function is basically quantifying your sense of oops, it didn't go well, isn't it? So loss function, from the loss function, you take the gradient of the loss, right? Then you back propagate, you do learning step, gradient descent, and you update the model. And so gradually this blue curve begins to get closer and closer to the data geometrically. And if you visualize it, it's beautiful to see how gradually from each batch of mini learning, this blue curve makes its journey towards the black curve, right? But if you stop your learning at a certain level, let's say you stop it at a certain level, it will be somewhere in the journey from here to here, it will stop somewhere. Let us say that it stops at the purple line, right? And somebody may give it to you at the purple line and say, okay, this is good enough. So what are the choices you have? You can say, well, I'm not happy enough with this, or I'm happy. My business is served. The practical reality determines what do you do with the model. When somebody serves you a model like this, you say that it has gone through free training. Now, here's a question that I'll ask you, a rhetorical question. why would the person who's training the model and making it available publicly want to stop and not go the whole route? Why will they want to stop?
Resource, right? More time is needed.
Krishna's answer, which is very practical from I can see the MBA strains, is that practical constraints
are no more.
Yeah.
Loss is improving.
That is right. Yeah. No, that is a correct answer and a very good answer. Practical reality is that you can burn only so much electricity and compute resources. At some point, you say, I stop. That is one part of the answer, resource constraint. What other valid answers are there?
You want somebody else also to contribute?
Overfitting? I don't know.
Albert believes that let somebody else also pull some of the weight.
Yeah.
And do the rest of the training. So that's an answer. What else? In fact, that's a good segue to the Roberta paper we'll study today. Let someone else.
I mean, no further improvement is coming by
also work.
Flatlined. Cannot represent the data in real life.
It cannot represent the data. Sanjeev has made a crucial point. I'll rephrase it differently. See, guys, there is only so much data available in the open source. When you trained large models, now let's bring it to our kind of transformer models. When you train it, you have access to a very tiny part of data. That part of data which is publicly available. You can use the common crawl. All of the internet data has been crawled. It's called the common crawl. You can take the Wikipedias, you can take the textbooks, you can take all that is available. So any data, if you think of it as one, and now this point is mathematical, and so please pay attention to this, because this is the heart of the issue. Any data has a certain probability distribution, right? So it will have certain, imagine that it has a certain probability distribution. Suppose it were two-dimensional, obviously these data are high dimensional, but let's say that they were two-dimensional. It will have a certain probability distribution, probability density distribution of happening, of just being true. So for example, if you're looking at all the animals in the zoo, you would agree that birds are far more probable, have a much higher probability density, are much more likely to be seen in a meadow. Let's not take a zoo, but a meadow that you happen to walk by, far more likely to be seen than, let's say, giraffes. Right? You might have a few giraffes, but that's about it, especially in our neighborhood. Right? So the probability distribution of the giraffes will be low, birds will be high, isn't it? And there was an interesting debate. Somebody once pointed out that the ants own the world. Why? Because there are far more ants than human beings. Then I pointed out that there are far more bacteria in just your body than all the ants in the world. So it goes on, right? So probability distribution, therefore, is unique. For a given situation, you have that. Now, what happens when you want to use this model in-house for your problem? What can be the problem? The model has learned from this distribution of the data, isn't it? But suppose this distribution of animals, this model is how to survive in that ecosystem, right? So what's the basic survival strategy? Yeah. You are the food to somebody and something else is food to you, right? So you have trained this model to optimally survive. When you change the ecosystem, you put that model now into a different ecosystem. Do you think it will survive well? No, right? It needs some adaptation. Are we together? It is as simple as that. The underlying assumptions of the data on which it has been trained are broken, partially broken, because the data, the reality is different. When the reality is different, your model will underperform, right? So therefore, even if somebody has infinite resources and contributes a really well-trained foundational model, that pre-trained model does not, it makes data assumption or has been trained on a data distribution that is likely to be different from your situation's data distribution, isn't it? So your situation's data distribution, all of a sudden, if you bring it to India, now you're talking about pythons and tigers, right? That it may not have seen. And so you need to adapt to that reality, the model. So that is the argument for fine-tuning the model. But when you fine-tune, you don't say, oh, I'm going to train the model from scratch. Why do you not train the model from scratch? Because there is a lot of learning that the model has already figured out. For example, it figures out that you see a predator, you run, right? And you see something that you can eat, you run after it, right? So that's the thing. The only thing it has to know now is this tiny little difference. What is the list of predators and what's the food available? Does that make sense? Right? Pretty much it comes down to that. Yeah? So a small bit of learning is there, but the harder learning of survival is still there. So a lot of knowledge is transferred. So I made it like that. But in real life, see, think about it this way. When you train a large, for example, natural language processing, when you train a model on a language, it has figured out the grammar. It has figured out the linguistic structure of the language. To train it has taken tremendous amount of knowledge, isn't it? After that, to fine tune is a small journey. You can do it with much smaller data. So this process, of course, we call it transfer learning. You can take a trained model, pre-trained model. That's why we use the word pre-trained model. So remember, most of the pre-trained model are trained to the best extent possible on externally available data. Why? Because those models are competing with each other. They have to show that on the benchmark they beat all the other models. Right? Otherwise, their model won't be popular. It's very much the winner take all society out there in the open source. Right? So you take a foundational model and then you fine tune it. So this process is called transfer learning. Right? You fine tune it. But that point still remains. People have found that even when you fine tune, because there are resource constraints, many of the times the foundation models have stopped training simply because somebody decided that 1 month of training is enough. And you can still go through more and more training of the data and make it better. But the foundational reason is that the distributions are different. Your purpose, the data distribution. The probability distribution for your purpose is different from the probability distribution of the data on which it was trained. That's the foundational reason. Are we together, guys? So that is fine-tuning of the model. Now, there is another very significant difference. It's the size of the data needed to pre-train and to fine-tune. Right? And the pre-training takes generally vast. So pre-training, let me contrast this, training versus fine-tuning and versus in-context learning. These days, we do three things. Pre-training, how do you pre-train a model? How much data do you need? Typically, you need hundreds of billions of instances of data. When you take a model, a foundational model, and that begs the question, we keep throwing this word foundational model. It actually, I think Professor Fei-Fei Li at Stanford was, to my knowledge, the first one to use that word, foundational model, but it has caught on. What does foundational model mean?
Out of the box.
Out of the box, but then who put it in the box?
Albert. To do with the architecture, the first model that was trained on the advancement of the architecture.
So why are all pre-trained models foundational models?
Trained on public data.
trained on public data. Okay. Yashika?
I think like the point of foundational models is that you should be able to effectively use them in low shot or zero shot contexts, like almost any context. And the other big thing
almost any context, you hit upon that. That is the word, yeah.
Yeah, and the context that they can be used in is like largely defined by the data sets that they were trained on, which are like giganormous. Like if you look at say SAM, it's literally like the largest picture database like in the West, possibly like exceeded by like projects that are being done in China on
That's true. That's true. So Yeshila Bodak made quite a few interesting points, and I'll repeat everything she said. She said that foundational models are trained on a lot of data, ginormous amounts of data. She gave the example of SAM, segment anything model. Do you guys remember we did that in LLM-1, segment anything model, the Facebook? How did Facebook train it? Well, it has access to perhaps one of the largest cache of images, because it seems that humanity eats, sleeps, and then posts pictures onto the Facebook, right? So is that, and the only thing perhaps bigger than that is China's database of pictures, because it's a surveillance state, right? So that's true. One thing is trained on ginormous amounts of data. The other aspect also she mentioned and hit the right point on was, and that is more crucial actually, is that when you build a foundational model, you built it in such a way that it is successfully able to do a whole family of tasks. Right? So for example, if you're talking about natural language processing, it will be a good classifier. It will be a good ability to it will summarize, it will have the ability to tell entailment, like does the second question, the second statement, does it follow from the first, right? Or is it a natural continuation? Or for example, is it a non sequitur, irrelevant to the first premise, right? Is it an answer to the first question? Is it the answer to the question asked in the first statement? Things like that. These are all examples of natural language processing tasks. And the foundational models are built to be versatile, to be able to address most of the common tasks. You'll see that. We'll cover the bird paper. You'll see that. You always train a foundational model to be applicable to a variety of tasks. So then the whole question comes, if you want a foundational model to be able to solve a variety of tasks, how in the world do you train it? You have to train it on one task, right? Which of the 6 tasks do you take? Do you take summarization? Do you take classification? Do you take question answer? Do you take entailment? Like, does this follow from the other or not? What particular task do you take to train it? What's the answer to that?
Generation.
What's the opposite of all of them? None of them. Right? You can't. Think about it this way. If you were to give it a classification task, do you think you have the ability to create 100 million text and their target labels? Yeah. You know, if you know engineers, any one of you who have ever run AI teams, as I've had the misfortune to do, right, lead AI teams, the first rule you know is engineers are too clever for their own good. Right? For every problem, they have only one solution: cleverness. Right? So when you ask them to create data, label data, they will do everything except create label data. They will not sit down and create label data. In my entire history, I have worked on what you today call machine learning or AI or data science or numerical computing and so forth. I have spent more than 3 decades on it. Worked doing particle physics on CERN data, worked for NASA, worked in corporations, worked everywhere. And yet I am still looking for that one engineer who says, goodness, this is CS. Let me sit down and create some good training data. I'm yet to meet that engineer. Right? They don't exist. They are unicorns. So to create training data, you have to go to people without engineering degrees. and then create. That's what I used to have. For example, in my previous company, I had a team much bigger than engineers to create just label data for me. It's very expensive, very, very expensive. So how in the world are you going to create a trillion data points or hundreds of billions of data points for classification? You have no chance. Even if you create it, it will be deeply flawed. Right? So what do you do to train this model? You realize that this is a question. You want to train it. You want to make foundational models. You're all ready with your GPUs. NVIDIA stocks, you just pumped it up because thanks to your sales purchase order, right? What do you do now?
Is it called semi-supervisor? No.
What do you do?
Predict the missing words. Like,
Come again?
So basically, loss function, you put it back and do all the cycles
Nothing.
again and again.
If you ever run this foundational model training, you realize that by the time the loss function begins to asymptote, flatten out, right? The power company is celebrating. The GPU company is celebrating. Everybody is celebrating.
People has their own power stations for their
That
data
is true.
centers.
That is true.
Bring the new content.
Okay, guys, I'm asking you a hint. I'll give you a hint.
self-supervised.
Classification doesn't work. What other way can you train the foundational model?
Continue to write the content.
Come again?
Continue to write the content.
Write the content. I told you, engineers will do anything. They will go to the bulletin, but they will not create label data for you.
Generate the content.
All engineers try to generate the content. It doesn't work. Anybody would like to vouch for the fact that engineers' clever generated content is bad content for machine training?
Yeah, of course.
Right.
What else is there?
So basically, I think it's discrimination that this answer is wrong, this answer is
I
wrong.
think like
How would you know? How would you train the discrimination? It's a bootstrapping problem.
for the large one.
So, guys, any other ideas that you have? It's a very basic question. We are surrounded by foundational models. We should know how these foundational models are trained.
Hire people with low wages.
Hire people with low wages. I am told that ChatGPT, OpenAI, has an army of Nigerians working for $1 an hour or $1 a
Is that
day.
true? I heard
It's true. It's true.
Data augmentation.
Asif, self-supervised learning.
How would that happen? How would that happen, Jay? Self-supervised.
So let's say it has the data. It'll try to predict and at the same time validate itself.
But then the whole question is, how do you train that self-supervised algorithm to be good enough to predict good data?
The data augmentation.
How would you train the AI model to be a good data augmenter? That is a generation task. I mean, see, images you can do. You can crop the image, rotate the image, do things. Let's stick with natural language for a moment. How would you augment the natural language? You need a generator model. How would you train that generator model? It's the old question, right? All the mice decide that what if we could bell the cat? But who's going to bell the cat?
Use another LLM to create data. So
Albert's situation is get another LLM to create the data, but who's going to train that LLM? So guys, the answer to that is that you ask this question, we have unlabeled data. How do I make it into labeled data?
So the $1 Nigerians.
$1 Nigerians, they're not enough in the world. Right. By the way, now India is becoming huge. As you know, there is an organization in India that said, this is a perfect meeting of needs. People want labeled data. India has a huge unemployment problem. And actually, one of the big things that's happening is India is becoming one of the world's largest and most productive powerhouses in data labeling.
Yeah, I know. Yeah.
So anyway, so I'll tell you this thing, guys. So this problem is called, here's some clever tricks. And in fact, this is how you train this. Suppose I say, right. And what I do is I go and do this. I go and mask this. I mask this, hide this. So the statement now becomes the jumped over the moon. And then I keep the answer here separately, cow. And I ask this machine to, given this sentence, produce this output, cow.
That's engineering hack.
It's a hack. Yeah. So do you see, guys, that the world is full of text? I can randomly go mask a word and then ask it to predict that word, because this word belongs to a vocabulary. Right? These days, you typically take a vocabulary of 250K words, let's say. Right? Roberta vocabulary, for example, is in 250K words and so forth. It belongs to, by the way, this epsilon is the belongs to symbol to a vocabulary of 250K words. It's one of the words, so you have to predict one of the words. Now, if you know classification, you know that the bigger the target space, the more data you need. So to train this model, you would need tremendous amount of text. Fortunately, human beings are a garrulous community. There's a lot of thinking and talking that's been done. And so you can take all the text and train it. Do you see this? What you just created is a masked language model. There's an old word for it. I think it used to be called it close. Right? This process was closed. So MLM, masked language model, right? In which you say, okay, now let's go train it. So do you notice that it isn't trained for any of the practical purposes? It's trained for a useless purpose. So you say, why in the world would you train a foundational model on something so useless as this? And the answer to that has that, see, think about it a little bit. And here's where the genius comes in. There is no way it can predict the cow here unless it knows a lot about human language. It knows its semantic structure, its grammatical structure. It has to know a lot because it's choosing this cow as the one possibility out of 250,000 possibilities. And for it to reliably predict cow, it needs to know a lot as a machine, isn't it? It needs to know the linguistic structure. It needs to know a lot about human languages. And therefore, you end up with a machine that has been pre-trained to understand human language at that moment, isn't it? And if it understands, then it's a short journey from there to whatever task that you give to it. Right? And so you will see, as we'll do in the paper that we are going to cover in a little bit, that models that are trained like this, they actually, the first model we'll do is the bird paper, which by now is practically the Genesis. It's like reading the chapter Genesis in the Bible. It's that old now. You will see that off the bat, it became the state of the art on many of the natural language processing tasks. So today, here is the scope of work today, guys. First, I'll explain a couple of research papers. I'll explain a bird led to a whole ecosystem of bird-related models. There was bird, then somebody distilled it. What's the process? What does distilled mean? Do we remember, guys, what does distilled mean? The student-teacher approach, Jeffrey Hinton's paper on distillation. So you can distillate the bird to make a smaller bird called the distilled bird. You can scale it up, right? One of the realizations was, so distilled bird, you remember, did almost as good as bird at much smaller the size. In fact, in some counterintuitively, in some benchmarks, it even did better. But that also spoke to the fact that the original bird wasn't very fine-tuned, very well-trained. Then came Roberta. Amongst his core messages was, and I'm just giving you a summary here, amongst his core messages was that, hey, hyperparameter tuning matters. If you hyperparameter tune bird, it gets much better. Also, let's train it a little bit more carefully. Let's make it bigger. Let's make the training longer. And let's train it with more data. All of these things. And then it gives you superlative performance. Are we together? And then came some other small variations of it. Like, for example, the deburter. Deburter basically said something very simple. It said, hey, if you remember the original transformer architecture, we were putting the embedding and the position. If you remember the original, the attention is all you need. You will remember position was hard-coded. Remember, there was a sine function that was used to compute the position embedding of the word. And it was a fixed embedding. In subsequent years, people didn't use fixed embeddings or even the word embeddings straight out of the box. Everything became learnable. Word embeddings became learnable, right? The position embeddings became learnable. So the contribution of, lots of small good contributions came. Deburter, for example, made a point that let's not concatenate or the position embedding and the content, the actual word embedding. Let's not mix the two up. Because what the machine will do is, if it tries to learn it on its own, it may actually take shortcuts. So force it to learn these differently, and it changed the attention formula. So we'll cover that also today. Now, each of these makes little contributions beyond the BERT architecture. How much contribution it makes and is it actually useful for your problem depends on your problem itself. Right? But BERT led to a whole revolution of encoder models. Today, we are going to cover fine-tuning of the encoder models. But before we do fine-tuning, I'm going to speak of two libraries, guys. One of them, and you should by now be very familiar with it. You have done it, but we are going to go back to basics and do it again. One is PyTorch. One, of course, is Hugging Face Transformers. Now, you may say, hey, I know all this like the back of my hand. And my answer is prove it. Right? So, in particular, only the transformer library within Hugging Face, not all of it. And we'll just focus on that. PyTorch, to whet your recollection, is the dominant library to create neural architectures. Those of you who are taking the Tuesday course, of course, you'll be creating a lot of neural architectures using PyTorch. But here, I'll introduce you. So I'll give you a task, which is building a model from scratch. And I'll give you a very simple task. I'll tell you this task. Suppose you are given two numbers, x1, two numbers, and x2, they are the input. So they form the x vector. Two numbers, simple numbers. Create for me, and by now, this is just a review of PyTorch. You have to build the model from scratch. Don't download something, don't do anything, right? You need to create a model, PyTorch model, as in code, create a model. And the generalization of this is xn, right? It will answer one of two questions. For classification, it needs to tell, what should it tell? Okay, it should tell whether the sum of these numbers. Okay, let me give you a set of tasks. These are very simple tasks. Classification task is any of them negative? So if any component is negative, it should come out as negative. Is that an easy one? Right? True, false. B, it should tell if sum is greater than, pick a number. 100 or some constancy. Whether the total is greater than 100. I'm deliberately creating examples that you can't find solutions to on the web, right? But these are still very easy examples. Can we do that, guys? Classification. Now, right?
So can
And
you
for regression, for regression, I want you to do these things. A, find, predict the total. Predict the total. B, predict the average. Let's see if you guys can do that. Average and standard deviation. Actually, I'm surprised. Why are these examples never quoted in any of the textbooks that I've seen? For some reason. Okay. Because these are fun exercises. Predict the average, predict the total, and find the max. Right? This you can treat the max of xi.
Why are you saying predict and not find?
Well, models predict. Right? So, guys, you can do this. Hint, you cannot use mathematical formulae. Right? So you can't just say, okay, here's a neural network, and by the way, here's my formula to use that. You have to train a network from scratch, an unmathematically trained network. Right? These three parts.
Hey, Asif, can I ask a question? Satyam here.
Yes, go ahead, Satyam.
I mean, I'll share this with you. I don't know about the rest of the team, but I'll fail miserably at this task. I don't even know where to start.
That's the whole point. That's the whole point, guys. I will walk you through, Satyam, now how to start. Right? I'll walk you through.
No, so Asif, I'll actually put out a request. I don't know what other people feel, but I would really appreciate if you walk us through one solution.
Absolutely.
Right?
Absolutely.
And my point is, like, I would go looking for the next 3-4 hours and I will not get anywhere. If you walk me through one, I guarantee you I'll solve all of them.
Okay, I'll walk you through all of them. But the only thing I won't do is show you the code. It's very easy, but I'll hand walk you through the code. Does that seem fair?
You can do code walkthrough.
Guys, we live in the world. I mean, what has the world come to? First, people used to go to Stack Overflow for solution.
Yeah.
Now they go to ChatGPT for solution. Please don't use ChatGPT for this. Right? Okay. My daughter told me something very interesting. So government officials are not supposed to tell that Friday afternoons are off. So at NIH, National Institute of Health, right, there is a code word they use. Right? And here's the code word. If you every Friday you'll get a email, right, saying Happy Friday. And whichever way it is, it depends upon how happy the director is. People can leniently leave a little bit early. So if it has Happy Friday, well, maybe if you disappear by 4:30, it's fine. 4 is fine. If he says Happy Friday 2 hours before, if he says a really Happy Friday, like 3 hours before, and it's become a tradition and a code word at NIH. So when I say please don't use ChatGPT, I'm not using code words. I mean, don't use it.
That means you use it.
Okay. So, all right, guys, let me give you the scope because the lunch has come. I will walk through this. To Satyam's point, I definitely will. But guys, do you realize that we are changing pace? We are now becoming code heavy. Right? This is your first problem. And I deliberately crafted a problem that you can't just download a Hugging Face model, or can you? Hugging Face model to answer this question right away. You won't be able to, right? Because I want you to learn to code networks from scratch. Here is a second problem I'll give you, which is really a fine-tuning. So this is training a model from scratch. Isn't it amazing that most people, and I also gave you a model in which it is obvious how would you create training data. Can you create 100 million training data sets or 1 million training data points for this model? All of these. It's trivial, right? This is something you can generate data for very easily. What is your network looking like? So this is the full training. Let me just call it full training. And its only purpose is to make you strong with PyTorch. Right? That is becoming rather a scarce ability these days. No, just use PyTorch. Right? Now, the second part is, then from there, we'll go to fine tuning. Right? We'll go to fine tuning. And by the way, while you're at it, see, a part C for you, which will be a little bit hard, it's tricky, and it will have an error rate, which says any primes it will answer this question, is there a prime? Right?
Asif, I have a second question.
Mm-hmm.
So let's say we code up this thing which says, okay, find the total. Okay, we implement a regression model and we get the total.
Mm-hmm.
And then we realize that, hey, it's actually making mistakes.
Mm-hmm.
And that's why we will do fine tuning to kind of improve the accuracy. Is that the intent?
So the Satyam, your answer is right. Is right and wrong. See, you will further train the model to diminish the error rate. Right? We use the word fine tuning, Satyam, when we say that a foundation model has been pre-trained on data whose distribution is different from our data. Right? So quite often what happens is you train a model, you take a pre-trained model, you fine tune it on one data, right? Usually when you fine tune it, you might end up fine tuning it on a data that's very clean, Satyam, for example, right? And it works just fine. But the moment you try it on a real world data, a different data set, then it may not work. So what it means is it needs further fine tuning. Every time your data distribution is different from what it was trained on, the probability distribution is different, you need to fine tune it again. Because the only thing machines can do is it can make good predictions on a given data distribution. Within the data distribution, it will work. Outside it, it will never work.
No, makes sense.
Yeah.
Let's say as we are building the concept, right? So let's say I take a problem which is find the total.
Mm-hmm.
Okay, let's say we build the model.
Mm-hmm.
Now, why would I fine tune this model? Is it because it's giving me a wrong answer, or am I asking it to say, well, now also find the multiplication of it? What is the job of fine tuning
I'll
in
give
a
you an
simple
example.
case?
Suppose you said find the sum, and people who generated the numbers only generated small numbers, or they trained it only with positive numbers. It worked just fine with positive numbers. And then you realize, oh, the world also has negative numbers, or this model wasn't trained with ginormous numbers, right? Or it wasn't trained with very small numbers, tiny numbers. Out of distribution data, when you encounter, you need to fine tune. That's one way to summarize it. Right? You fine tune always when you have out of distribution data. Okay? The other way to look at it is to be suspicious. Was it even trained enough? Right? So I'll give you an example. I asked somebody person in my team to just write a simple classifier, fine tune a classifier, literally today morning. This is as of last night. To fine tune it against a text categorization between three classes. Right? Text could be, let's say, technical. It could be stories. It could be, let's say, legal, since we're talking about legal in the moment. Right? And you do the classification. The person who data was accessible took a model, PyTorch model, and went through the fine-tuning process. The person stopped at one epoch. Can you guess why the person stopped at one epoch in my team?
Because the results look good?
No, the accuracy that we were getting, prediction accuracy, was just 40%.
Because that was the default value?
No. The reason the person stopped is hardware resources, to Krishna's point. That person sat on it for 6 hours, and on that, the laptop, yeah, at the end of it, he just got tired and went home. It being a Friday evening or Saturday. What is it? Friday evening, Saturday. Ultimately, he had to go out with the family.
Even the coin toss has accuracy 50%. So if you are getting 40%.
No. It was a 3-class problem. So for 3-class, 45, actually it was high 40s, around 50%.
If you are getting less than 50, then just go home.
Just go home, yeah. Now, what did I do? So to your point, Satyam, all I did is take exactly the code, ran it on this NVIDIA 4090, right? Within a few minutes, what is the terminal accuracy on exactly the same data? Make a guess, any one of you.
7.
You can just walk over to my screen and see it's running there. It ended up at 97%, right? Without changing the data, without changing the code, without changing anything. So this speaks to the compute resource limitation, the point that Krishna made. Sometimes you need that patience to be able to run it, or you need to buy a lot of GPUs if you don't have patience.
Supal is happy.
Yes, Supal is going to sell a lot of computer stuff. Okay, guys. So, Satyam, does that answer you?
Yeah.
Yeah. So it is either the resource constraint, premature stopping of training, or you have more data to train it on. But the single biggest theoretical reason for fine-tuning is you encounter data that is out of distribution from the data that train the model. Because then you don't have a choice. It's like, you took an English-speaking person to Germany, and the person now can't get it. Can I tell a really bad joke or a dad joke? Right? So one day, the Brits and the Germans got together and they said, we need to have one language. So the German says, yeah, perfectly fine. We should have it. We are fine with English. We just need minor modification. First is, C is unnecessary. Let's put K there. Right? And then, so culture became culture. Yeah. And then some more and more small modifications. And by the time the Germans were done, the language looked German. So that is what I would call a perfect real life example of fine tuning English.
Asif, can I ask a quick question? So
Yes.
I was actually having a conversation with a major pharmaceutical company who is investing or already been working on this transformation journey with $600+ million already being going on there. So one question I have asked was like, what type of an approach are you really taking from bringing in Gen AI? Are you fine tuning? Are you RAG implementing it? Are you building your own models? The immediate answer that I got was we are 100% RAG implementing because we need deterministic response because most of our use cases are around FDA responses and we cannot go with the guesstimations. So we need to have deterministic answers. So our temperature is always set at 0.9 or 0.6 or something like that. So the question that I have is that in the world of us, heavily going to be relied on these mega players with a massive knowledge base, aka the big models like OpenAI or Mistral or any one of them. Why would we ever want to fine tune if we have so much dependency on these models? That's been going on in my head.
Yeah. So first, let's unpack, Madhu, all that you said. What you said is the pharmacy company said they always go with RAG rather than fine tuning because they want deterministic results. So let's stop there. See, guys, and setting the temperature to 0.6 or 0.9. Actually, 0.6, 0.9 will not give you deterministic results. Even if you set in an LLM the temperature is 0, what did we learn today morning? It will still
creative.
So whosoever is there at the head of that pharmacy is again one of I call Google Scholar machine learning experts. They need to come in courses here. The second part is you do RAG because you want to protect your IP. Remember, you don't want to teach your IP on the feed your IP into the LLM fine tuning, because then LLM knows it. And LLM is like a child. It will blurt it out if you give it the right prompts, right? Somebody can steal your IP. So anything that is confidential or high valuable IP, you rag it, you never give it, right? Now, determinism is achieved to the extent that it is possible with a LLM through multi-agent or through multi-prompt, multi-stage answering, the way we talked about. It is not achieved through temperature. It is not guaranteed through RAG. RAG only improves it, but you need to go through the advanced prompting techniques that I've been teaching you guys in this workshop. That's the broader answer. Arul.
So this is a good explanation, like why RAG is not going to go away soon.
Yes,
it's here. Improved fine-tuning, improved training.
Yeah.
All the larger
right. See, so now the whole question is, if that is true, then why do you need to fine-tune the model at all? If I can
inference speed.
Yeah.
Inference speed.
Yeah, go ahead. Inference speed. Very good answer. That is one. What other answer is there? See, guys, not every situation takes RAG. Look at this problem. If this model has been trained to produce the sum of numbers, but only small numbers, how in the world can you rag your way out of it? Can you rag your way out of this? No, you cannot rag. So, guys, here is the thing that you learn. I used to be in a past life, in a past incarnation, a quantum physicist, quantum theorist. Our job was to figure out what was happening at the scale of quarks. Have you ever thought how tiny the quarks is? Or neutrinos are? Bazillions of them are zipping through us and we don't even know, right? And yet we could make predictions. And there's only one trick that human mind knows. Simplify every problem down to its essence. If you can simplify every problem down to its essence and reason from that, you'll always hit the mark, right? We can tell today precisely when the Big Bang happened. Just think of the achievements you get by simplifying and reasoning with simple models. I'm giving you what I put on the screen may look as very obvious problems or simple problems. There's a reason. I'm helping you reason with simple models. Ask yourself, look at any of the problems here. 3 classification problems, 3 regression problems. How can I rag my way out of it?
But these questions are mostly mathematical, and they're
LLMs can do math just as
it's not a generative.
Okay, then make it generative. Let's make it this way. Should I make you do another
logical expression? What I mean to say is the answers are either.
Okay, then go ahead and build a PyTorch model that tells you a named entity recognizer in this. Right? You can do that with this very simple code. It's a little bit harder code, but you can't drag your way out of it.
Sorry, can I make a point?
Yes.
I can't even solve this. Don't make it more complicated. Like maybe I'm really lagging behind here, but I can't solve a single one of these problems.
No, I'll help you guys. I mean, see, that's where we are. We'll figure it out in a moment. Yeah. Yashila, 1 second.
I'm going to what we were making earlier about how we train some of these other models. Like, wouldn't you just take the same approach and like swap or just try to predict like random polls like in the data, like the training data that you have is like a priming for going into the rest of it? Because that's how, like, I don't know. I feel like that would be kind of equivalent to like if there's some underlying structure of the data that you have to be able to kind of understand how like what's going on.
No, Yashila, you do that. And you brought up a very good point, namely, if you study the data distribution itself, you can literally identify regions where the probabilities are low, sparse regions. And then you have to ask the practical question, if the data is sparse there, is it of practical value that I have more data? And if there is practical value, then certainly you should get more data, and that becomes a strong case to fine-tune the model further on that data.
Right.
So that is that. So guys, so here's the thing, guys. Fine-tuning, right? You need for one reason only, primarily, because the real life situation you are facing, its distribution is a divergence from the distribution, data distribution, the model has been pre-trained on. That is a big reason. That is the theoretically important reason for it, because that is an inescapable reason for you to fine tune, no matter what you do. Go ahead.
Yeah, so for example, as if the image analysis, right?
Yeah.
The initial images which transformer needs to run, that time the fine tuning must have happened. And then the RAG can help solve close proximity matching.
Yes, it could do that, but I'll tell you one thing. It's one of the strange things that happens. I'll give you a real, the best way to answer your question, like for example, so let me Prasad has asked this question, that with images, the machine may have seen some images, and then when it gets new kinds of images, you can RAG it with new images, information retrieval. I'll give you an example where that won't work. See, it's a very odd thing. When I grew up, in a boarding school. Everybody was a kid. So I would immediately recognize the young faces. But all the grown-ups used to look exactly the same. Right? And when I was very young, when I was in my first grader, and the vacation started, I was in a state of panic. Will I recognize my parents when they come to pick me up? Right? Because really, all the grown-ups look the same. 1 year later, I didn't quite remember. Those were the days before photographs were so common, right? Fortunately, I spotted my father. Immediately, I saw him. So it turns out I hadn't forgotten it, but I was in a panic, right? Likewise, when I grew up and came to US, it was very hard. I could tell the faces of all Asians. It was very hard for me to tell one American native apart, a white Caucasian, apart from another white Caucasian. They look all exactly the same. And somehow I had to find a trick to remember them. So I used to call every one of them Jason. Right? And then they would correct me and then I would write it down. So you see this very real world I'm showing you, that when you meet out of distribution data, I needed to be trained. My eyes, my mind needed to be fine-tuned, to be trained, isn't it? A similar thing, I know a shepherd who swore to me that he can always tell the sheep, actually goats in India, goats. He knew the goats by heart. He knew everybody's personality. He could tell when a goat was sad and when a goat was happy. But he had such great difficulty remembering people's faces or remembering who was who in people, right? Again, an example of a well-trained mind that needed fine-tuning on an out-of-distribution data. He spent all his life in the hills taking care of the goats, right? So that is not something you can drag your way out of. It's fact. Even for images, it's a fact. Since you brought about this question about images, what applies to text applies to images too, right? So fine-tuning, again, I'll reiterate the main point. Fine-tuning is needed whenever you encounter a data whose distribution is divergent from the data it has been trained on. See, in machine learning, you use the word IID, right? Independent and identically distributed. Whenever you take a sample of the data for training or for inference, you presuppose a distribution. It must, all your samples, whether for training or for inference, must respect that distribution. The moment that there's a distributional drift, all bets are off. Are we together? And therefore, the rationale for fine-tuning. That's the most mathematical way and succinct way I can put it. Why you need fine-tuning.
And this includes bias correction, all that, right?
Absolutely, bias correction and everything. Yeah. So let me, because it's lunchtime, so guys, I'll walk through the code. But first, so today, let me finish it. Lots of questions. So guys, our journey this week will be, we'll build models from scratch, then we'll fine-tune models. Today, I'll also give you a fine-tuning problem with PyTorch and with Hugging Face. And because you are learning, this week, I won't wait too long to release the solution. I will release the solution practically by Tuesday, Monday, Tuesday. Does that look reasonable, guys? It just gives you 1 or 2 days to try it out on your own. And when I give you the solution, it will be a Jupyter notebook with lots of explanations, right? With lots of explanations. So you can just read your way through it. By the way, I must tell you that when I put this problem here, there are deliberately little traps in it. You can make a naive model, which will sort of work. And you can make, these are the best, this sort of problems are the best interview questions, because there is the same problems you can use to hire a junior engineer, and the same problem you can use to hire an engineer whom you're paying $1 million a year. Because the hint that I'll drop is, there are very clever ways of doing it. That will make you review everything that you learned in the deep learning, that Tuesday course that I'm giving. Some of you have taken it. Everything that you have learned there, you can use to solve it cleverly. Right? So do that, then I'll give you 2 fine-tuning exercises, both very easy, both dealing with the most common task in NLP, text categorization. Text categorization has a 25-year history to it. You'll fine-tune models for that. And we will walk our way through that, right? So that is the scope of the work for today, right? And I'd like to end, I know lunch is here. Thanks, Abhin. Lunch is here. And I'd like to end with one story that is told in Silicon Valley. And I don't know how true it is, but it's so common. It has a good lesson to it. So apparently once the defense forces, when the defense people, the US Army goes to fight, military goes to fight, they try to minimize collateral damage. Right? They don't want to hit civilians. They want to hit only enemy combatants or the enemies or so forth. Every sensible military would want to do that. So once they heard that the Silicon Valley blokes, they are up to AI. So they came to the blokes, apparently. So the story goes, and said, one outfit, and they said, hey, can you build an AI model that can tell apart a civilian vehicle from a military vehicle? Right? And those guys said, well, that doesn't seem like a tough problem. It's classification. We can do that. What do you need? And these guys said, just give us lots of pictures of civilian vehicles and lots of pictures of military vehicles. You can imagine those high-powered military guys saying, oh, that's all. We'll get that. And giving an order and everybody down the command line saying, sir, yes, sir. Right? And then suddenly huge boxes of pictures began to come out. The AI model was apparently trained and it worked perfectly in the lab. It could tell military vehicles away from civilian vehicles. And they demonstrated it to you can imagine some general with lots of things hanging off his thing, like looking rather impressed and then walking away and deploying it in the field. And it was a perfect disaster. It didn't work at all. And everybody was confused. How can it work in the lab and not in the field? The same algorithm. And the reason turned out to be, what do you think the reason was? Oh, some of you have heard this story from me. Okay, you can't say. So I'll tell you this. This is again the subtle biases in the data, and that's where you would need fine-tuning. What happened is that you ask military people, personnel, the army soldiers, to go take pictures of civilian vehicles and military vehicles. Guess when do they meet civilian vehicles? They are out on a beat, right? So imagine them sitting nicely on their Humvee or on top of their Bradleys and going through the streets of some city, and they see civilian vehicles all around. Click, click, click. Throughout the day, they take pictures. Then the day is over. It's evening. They come back to the base, right? And when do they encounter military vehicles? Either early in the morning or late in the evening, right? So what is different between these two circumstances? Ambient light, right? And so all the pictures of military vehicles were taken during very early low light conditions or late evening, low light conditions. And all the civilian pictures were taken in broad daylight. And guess what the AI latched onto? Ambient light, isn't it? And that is a problem.
How did they miss in the testing phase?
Because you would just do a test train split and it's the same box of pictures that you have done test train. So the story, guys, I don't know how real the story is, but it's certainly a very entertaining story that's been told in Silicon Valley over and over again, right? So, and therefore a case for fine-tuning that model with better data, because real life data distribution is different from what it was trained on. Yeah, go ahead.
Asif, somehow, is this the only thing for this week? If that is the case, then it looks simple.
Oh, it looks simple. Nice. Yes, this week it is all fine-tuning, guys. This week we take baby steps at fine-tuning. Next week we do next couple of weeks we do advanced fine-tuning. Today is just literally not even fine-tuning. The first exercise is to build a simple model from scratch, and then 2 exercises in fine-tuning. Right. But yes, this is a start. So guys, let's take lunch. I'll stop the recording and I'll take questions right then. Then we break for lunch and then I'll walk you guys through the code, how to do it.
So Asif, I was trying to schedule some things. Are you taking off this coming Saturday, Sunday?
Oh, yes. Guys, thank you, Sachin. Thanks for reminding me. Guys, a big announcement. I will be going to Carnegie Mellon for my daughter who got admission. She seems to be in 2 minds. She says, I have such a good job. Do I really need to do grad school? I'm hoping she agrees to. So I'm biased. Anyway, I'm taking her to Carnegie Mellon next week. So next Saturdays, I won't be here. I'll be in CMU.
There's a lot of time to do the fine tuning then.